Let's look at how stars produce their energy because in the last video we saw that within the core of this protostar, which has now become a star, hydrogen nuclei are fusing together under the influence of the strong force into helium nuclei. Four protons are converting to two protons and two neutrons in a helium nucleus. But what does that have to do with energy production? How do you get energy out of that? We had no idea until 1905, when Albert Einstein not only completely changed our understanding of space and time, of matter and energy, but actually explained how balls of hydrogen can generate as much energy as stars give out. The clue, the secret, comes from the fact that when you fuse these four protons together and convert them into two protons and two neutrons that are held together in a nucleus, you might think, well, the same amount of matter is present. It's not like we've removed any matter, but in fact, the four protons that you started with weigh slightly more than the resulting helium nucleus. Some of the matter of the original protons seems to have disappeared as what we call the mass defect. It's a very, very small difference, about 0.7% of the mass of each nucleus seems to disappear. In fact, it doesn't disappear. It converts to pure energy as special relativity predicts according to equals mc squared. So in fact, what happens is you have the matter of these four protons, you convert them to two protons and two neutrons, but a little bit of that matter converts to energy. That was where that gamma ray that we saw in the proton-proton chain comes from. And this little tiny mass defect converts to pure energy to power the sun. And that is our modern understanding based on special relativity and E equals mc squared of how stars are powered. There's only one problem with this idea, and that is that it doesn't work. Or at least it doesn't work according to a classical understanding of physics. Because according to classical physics, if you do all the thermodynamics and everything like that, even at 10 million Kelvin, protons that are moving at about 5,000 kilometers per second are still not moving fast enough to overcome the electromagnetic repulsion between them and get within femtometers of each other. And if they can't get within femtometers of each other, then the strong force can't kick in to hold them together, and there will be no nuclear fusion and no mass defect that will release energy. Now, if this were true, according to classical physics, the protons need to be at a temperature of at least 10 billion Kelvin, not 10 million, but 10 billion. And here's the problem. Remember that all that raising of the temperature is coming from gravity pulling the matter closer and closer together. And the more massive the nebula is, the more gravity it has, so the more it squeezes on the matter and the more it heats it up. But there is no nebula anywhere in the universe as far as we can tell, and as far as physics would tell us, that will have enough mass to have enough gravity to squeeze the nebula up to 10 billion Kelvin. And if you can't get it to 10 billion Kelvin according to classical physics, you cannot have nuclear fusion. And if you cannot have nuclear fusion, you cannot have stars. So what's the answer? Well, the answer comes from quantum theory, from modern physics. Because remember that protons are not only particles. We need to look at protons through wave-particle duality. And remember that idea of quantum tunneling, that particles, what we think of as particles, can go places as waves that they couldn't go to as particles. And so the protons as waves can occasionally collapse into particles within femtometers of each other. And then the strong force can kick in. And in fact, quantum theory predicts this to happen in just the right numbers to produce just the amount of energy that we see coming from stars. So without modern physics, without the wave-particle duality of quantum theory, we wouldn't actually be able to explain the power of stars. Let's look in the next video at what happens once the nuclear fusion in the core of our protostar begins.